Okay, so in this video I'm going to give you a quick revision on chapter 5 of the book, which is on forces and uniformly circular motion. So if we want to start with the basics on forces, we know the force is an interaction between two objects. Now, the first thing that is useful in the study of forces is making a free body diagram, which is a drawing of all the forces acting on an object. So this is a drawing of all forces acting on an object. So we can draw an example here. If we have an inclined plane and there's this box over here on this incline, then we can draw the forces. The free body diagram for the box here will show us a weight force, a normal, which is always perpendicular to the surface that is exerting it, and a friction, which is always opposing the direction of motion or the tendency of motion. So this is a free body diagram. Sometimes in a free body diagram, you can represent the object with a point so that you can draw all the forces from the same point. This is useful when you want to find the resultant, for example, or when you want to study the projections of the forces on the x and y axes. This is actually the second step of the study of forces, which is finding x and y components of forces. So usually when we are studying forces, if we have linear forces, these can be added or subtracted directly to find the net force acting on a given object. While if the forces are not linear, we will not be able to add them or subtract them directly. So first, let's see an example. If I have, for example, this box, and it's on a surface, and two people are pushing this box with a force F1 and a force F2, then we can directly say that F net is equal to the sum of F1 plus F2. And we can deduce the acceleration, for example, by saying it's F net over the mass of this box. And if they have opposite directions, then we just subtract them. While if we have nonlinear forces, these cannot be added directly, so we have to study them by finding their x and y components. So let's see an example. If the same box is on a surface, now one person is pushing it with a force F1, while the second is pulling the box with a force F2 that makes an angle of 60 degrees with the horizontal. In this situation, the two forces are not linear, and we need to find the net force by considering the x and y components. So how do we do that? We draw the forces starting from the same point. Basically, we are drawing the free body diagram. So in this situation, F1 is pointing to the right and F2 is making an angle of 60 with the horizontal. Now what we do next is that we select our x and y axes. So in any given problem, we start by drawing an x-axis of our choice and a y-axis that is perpendicular to the x-axis that I have chosen. And once I draw the x and y axes, I look for the x components for each force and then the y components, and I add them separately to find the resultant force. So for F1, F1 is along the x-axis, so its x component will be the force itself, while its y component will be 0 because it is along the x-axis, so it does not have any component on the y-axis. Now, let's assume here in this example that we are given F1 to be equal to 3 newtons and the magnitude of F2 is 4 newtons, so that we can find a value for the net force. Now, if we look at F2, F2 makes an angle of 60 with the x-axis. If we project F2 along the x-axis, we can find its x component right here. So this is F2x, while this is F2y. This is the y component of F2. Now we can find F2x by doing some trigonometry. So if we look at cosine the angle 60 here, this is adjacent over hypotenuse. The adjacent side here is F2x and the hypotenuse is F2. So we can deduce that F2x is F2 cosine 60. And we can write a general expression here actually. The x component is equal to the force times cosine the angle it makes with the horizontal. So for a general expression, Fx is always equal to the force itself times cosine theta, with theta being the angle F makes with the horizontal. While Fy is going to be F sine theta, and theta again is the angle that the force makes with the horizontal. So now we found a general expression for Fx and Fy. In this situation here then we can write that F2y is going to be equal to F2 sine 60. And from these two expressions for the two forces, we can find F net x, which will be the sum of the forces along the x direction. So this is F1x plus F2x. And this will give us F1 plus F2 cosine 60. And we can just substitute the values we got and get a final answer for the x component of the net force. F net y will be the sum of forces along the y direction. So this is 0 plus F2 sine 60. And again, we just substitute. So this is 4 times sine 60. And we can calculate the values here. This is going to be 5 newtons. And this is going to be 2 radical 3 newtons. We can find a decimal value for this answer. Now we found the x and y components for the net force. What we can do next is that we can find the magnitude of the net force. From the x and y components. So the magnitude of the net force is equal to radical Fx squared net plus Fy squared net. So the x component of the net force that we found previously here, which is 5 newtons, it should be squared, and we add to it the square of the y component of the net force, and then we apply a radical to find the magnitude of our net force. So here this is going to be radical 5 squared plus 4 times 3, and we can find the magnitude of the net force. We can also find the direction of our net force. Because forces are vectors, then any force has to be characterized by a magnitude and a direction. The direction can be found by finding tangent theta, which is equal to f net y over f net x. So we can just apply this in order to find the direction of our force. So here f net y was 2 radical 3. And f net x is 5. So this is 2 times radical 3. This gives us 0.69. And we apply the inverse of the tangent. So this will give us an angle of 35 degrees. So we basically study forces and apply x and y components, and then we apply the sum of forces to find a given net force. Now, sometimes we apply Newton's laws instead of just finding the net force. We can apply Newton's laws to find the acceleration, for example, rather than the net force that we are interested in. So let's recall the formulas for Newton's laws. Newton's first law says that the sum of forces is equal to 0 if the object is at rest or if it's in equilibrium. And this means that it can be in constant speed, for example, and then the sum of forces will still be 0. While the second law says that if the net force is not 0, then it's going to be equal to the mass times the acceleration. So this applies to equilibrium. And here we say the forces cancel each other. While here we have a net force. Which is different from 0. Of course, here f net is equal to 0. And the acceleration is equal to 0. We also have Newton's third law, which is the principle of interaction. So for any force exerted by any object 1 on object 2, there is an equal but opposite force exerted by object 2 on object 1. So if we have someone standing on Earth and Earth is exerting a weight force on this person, this weight force can be also named as F Earth on this person. And this person will exert an opposing force to this weight. He will exert a pull on Earth equal to that exerted by Earth. Earth, however, doesn't move because its mass is much bigger, so there will be no acceleration due to this force, while the person has a much smaller mass, so exerting the weight force on him is going to cause him to fall, for example, if he is not on the surface of Earth. So basically, this is a summary of forces, basics, drawing free body diagrams, finding x and y components, and then using these components to find the net force. If you are interested in problems on these concepts, you can check the playlist here, which contains a few problems on Newton's laws and how to find the forces by applying different formulas.